that is needed for a standing wave to be created.
This call is now being recorded. This call is now taking notes.
So what are those conditions?
Amplitude.
No. Guys, someone else should help you. So to the question. So who will come to the rescue? Lucas. Lucas, were you in the last class?
Good evening, son.
Okay, good evening,
Yes.
Lucas. What are the conditions required to create a standing wave based on what we did last? Okay. Well, in order to save time, so we can go straight to what we have for today. Because today we won't be looking at wave. I will actually come back before we round up this session. Your physics exam is still. When are you starting your exam again, please?
On the 20th of this month.
When are you having physics? 20th.
No, we are starting the exam on the 20th with chemistry practical.
So when are you going to have physics theory?
1st June.
1st of June. Okay. All right. So from now to then, we'll still touch few other things that you need to know. Meanwhile, the answer to the question I was asking you before, the condition necessary to create a standing wave include: 1, the wave must be traveling in opposite direction. That's the first condition. Secondly, the wave must have the same frequency. And thirdly, what did you say? And thirdly, the wave must have the same amplitude. So those are the things we talked about. But today, I want us to be looking at, or to look at, electric field. Electric field. So I'll try to be swift. Usually, as I do say, the things I'll just go straight to the point, and then if there are points you miss, you can always go back to the video because I will always upload it. So today's class is electric
After
field.
chemistry is fifth.
Okay. Obahomi, your network is usually disturbing. All right. I don't know why you respond like up to 30 to a minute the question has been asked. But that's fine, no problem. 1st of June, no problem. We'll see what we'll do before then. Now, what exactly is electric field? Let's start with that. What is electric field? Electric field is simply, also, who can come to the rescue? Can anyone try? In 5 seconds. What is electric field? Okay. An electric field is simply a region of space where a charged body experiences an electric force. That's what it is. Electric field is a region of space is a region of space where a charged body experiences an electric force. So this is what we call electric field. It's simply a region of space where a charged body experiences an electric force. And this electric force, let's say I have a charged body here. Of course, we have two types of charges. This is my positive charge. Let me try to take it down a little. This is my positive charge. Let this be a negative charge. Now, usually, these two charges is
Francis,
going to
I'm
create
not
what we
seeing your
call.
screen.
Is there anyone else who cannot see my screen, please? Can everyone see my screen?
Yes, sir.
Obaomi is from your network, please. The screen has been shared. Everyone can see it. All right. So I have two charges right here. Now, usually, these charges is going to, two of them will create an electric field. And the motion or the direction of this electric field is such that it emanates from the positive charge and enters the negative charge. It moves off from the positive charge, enters the negative charge, from positive to negative, from positive to negative like this. So let me put the direction. So the charges keeps on going out like this, comes out from the positive, it's coming out from the positive, then it moves into the negative like this. It comes out from the positive. Let me draw another one here. Coming out, coming out. Then if I draw it right here, it's going to move in here, move in. So what I drew here is the interaction between two unlike charges. So if I bring two unlike charges, they will actually create a field. That region where the charged bodies experiences an electric force, which is the region. When we talk about the region, we're talking about every of this region here, because at this point, the two charges are interacting, all right? That is what we call electric field. And these lines I drew here, showing the direction of this electric force, is called electric line of force. It's called electric line of force. And how do you define electric line of force? Even though it's something that is not visible, you can't see it. But the electric line of force is simply, we call it an imaginary line. Of course, it shows us the direction of the electric force in the electric field. That is exactly what it does. So what the electric line of force does is that it shows us the direction of the electric force in an electric field. And clearly, this diagram reveals the interaction between two unlike charges. That's what we have here. And as you can see, the line of force comes out from the positive and then it goes into the negative. You can see the arrow indicating the motion or the direction of what? The force. It comes out from the positive charge, then it goes into the negative charge. That's what we have here. Then also, what then happens if I bring two like charges? If I bring two like charges, let's say I bring a positive and positive charge. So let's say I have a positive charge here. I bring another positive charge here. Of course, you know from the law of electrostatics, you know that it says that like charges is going to repel, unlike charges will attract. Just like you can see in this first diagram here. This is the interaction, this one here, interaction between two like charges, unlike please, between two unlike charges, unlike charges. So when the charges are like, what then happens? So let's say I bring two positive charge. Of course, according to that law, like charges will repel, only unlike charges will attract. So when the electric line of force comes out like this, it moves up. It comes out, it moves this way. They can't attract. The two forces cannot attract, or the two charges cannot, there can't be any force of attraction that would exist between these two charges. Why? Because they are simply like charges. So what I'm drawing here is just the electric field between two similar charge. So because the forces are always, remember the line of force always emanate from the positive, so it will be pointing outward, outward on both sides. This is also pointing outward, outward, also pointing outward here. So there is no inward. So because of this, the two charges will repel. So it comes out, then it moves up like that. And notice the way I drew the diagram. Between the two like charges, you can see that the lines are somewhat perpendicular. But when the charges were unlike, then it's more like a curve. It's curved. That's how the line of force is being drawn. All right. So when the charges are not the same, so we use curved line to indicate the line of force, and always indicate the fact that the line of force moves out from the positive and enters the negative. But when the charges are similar, then it will be more like a perpendicular line. It comes out, it goes up, it comes out, it goes up, just like that. And then of course, if it is negative, negative, the same diagram, the only thing that would happen is that the arrows is going to be pointing inward for the both charges. So this is the interaction between similar charge. So this is the interaction between similar charges and the first is the interaction between unlike charges. All right, remember I said the region, that region of space where a charge body experiences an electric force is called electric field. All right, so that is that for that. And now, how then do we describe the properties of this line of force? Because this line of force has properties. Remember, the line of force I said is an imaginary line that shows us the direction of the electric force in the electric field, which is exactly what I've shown using these two diagrams here. Those lines you see, the curved and the perpendicular line, is called line of forces. So what are their properties? We have properties of line of force. So let me indicate that properties of line of force. You might be asked in your exam to highlight 4 properties or even 5 properties of electric line of force. Electric line of force. The first is as seen in the diagram. The first one is that the line of force emanates, lines of force emanate from the positive, and enters the negative. The line of force emanates from the positive and then enters the negative. The second one, or the second property, is that the line of force do not intersect or cross each other. So lines of force do not intersect each other. When I say intersect each other, just like in this, just like having two charges like this, positive, let's say negative. So someone is drawing something like this, one coming out like this, then another one maybe just a kind of intersection, just like this here. So line of force, it doesn't matter their proximity, they don't cross each other. So that's another properties of line of force. The line of force doesn't cross each other irrespective of whether the charges are similar or not. Now, the third one is that the line of force are continuous in any region with free charges. So the lines of force are continuous in any region with free charges. In any region with free charges. The lines of force are continuous in any region with free charges. And then the third one, we also say in uniform field, the lines of force are uniformly spaced. So in uniform field, the lines of force are uniformly spaced. So let me add that up. In uniform field, the lines of force are uniformly spaced. And then also we say that the line of force are infinite. Or let me say this one, the lines of force shows the direction of the force in the field. So just like that, so many of them, I've given you up to 5. So let me just stop here. I can give you up to 8 properties of line of force, but we can stop it here. So firstly, we said the line of force, they comes out from the positive and then enters the negative. And then we say the lines of force do not intersect each other. We also say that the lines of force, we said they are uniform in a uniform, they are uniformly spaced in a uniform field. And we also said that the line of force shows us the direction of the force in the field. And then we also said that the lines of force are continuous in any region with free charges. So those are basically the properties of electric line of force, just in case you're being asked to name them. And don't forget that this electric line of force is simply an imaginary line that shows us the direction of the force in the field. That was where I got this last property I added. Okay, so that is that for that. Now, the next thing I want us to look at is potential difference and electric current. Potential difference and electric current. Potential difference and electric current. Now, what is potential difference? What is potential difference? Or maybe let me begin with electric current. What is electric current? Electric current is simply the rate of flow of electric charge in an electric circuit, or the rate of flow of electric charge along a conductor. That's what we call electric current. So you can write that electric current is the rate of flow of electric charge along a conductor. I repeat, is the rate of flow of electric charge along a conductor. That is what we call electric current. And current has a symbol. Usually we represent it with a symbol I. And if I'm to write this definition mathematically, we can say that I, which is current, is equal to charge Q divided by the time taken for the charge to flow. So this is how we calculate current in an electric circuit, or the current flowing along a conductor. If I know the charge is in coulombs and the time always in seconds. So let me write out the meaning, where our I here talks about the current, of course, the Q is a charge, and then our T is time in second, the charge in coulombs, and of course our current in amperes. So these are their units. The unit for current is amperes, charge coulombs, and time must be in second. And clearly from the first equation, which I want you to take note of, because all I'm trying to do here is to build up equations that will be used in solving problems involving electric field. So this is the first equation here. Okay, and then from this first equation, if I try to cross multiply, you will see that Q is equals to I times T. So from equation 1, we can see that Q is equals to IT. So meaning that if you know the current and the time and you want to know the charge, you simply get the charge by multiplying the current and the time. But if you know the charge and you know the time you want to get the current, all you need to do, divide the charge by the current. That will give you the rate of flow of the charge, which is called electric current. Okay, so that is that for that. Now, the next thing I want you to learn or want you to know is the potential difference. Remember, I said the subheading is current and potential difference. What is potential difference? That's the question. Potential difference. The symbol for potential difference is V, capital letter V. Potential difference is simply the work done in bringing a unit charge from one point to another point in an electric circuit. So this is the work done. The work done in bringing a unit positive charge from one point to another point in an electric circuit. Remember, every conductor has electrons. They have charges that are domiciled in it. These charges are there, but the charges are not in motion. But anytime electrical energy is being supplied, what happens is that the charges are being set in motion. Of course, when we say work done, work is said to be done anytime an object or a particle moves from one point to another. So if electrical energy is being supplied to the circuit or to the system, the charges begins to move. That work that is done in bringing one unit positive charge from one point to the other is called potential difference, and it's been written with symbol V. And mathematically, we can actually calculate potential difference. But before I give you the formula, take note of the fact that this potential difference depends on the electromotive force of that cell. The electromotive motive force, or the EMF, before I bite my tongue, electromotive force or the EMF of the cell that is being connected to the circuit is what determines the potential difference that flows through the circuit. So I can say that the potential difference depends on the EMF. Remember, EMF means electromotive force. The EMF of the cell connected to the circuit. Of the cell connected to the circuit. Somebody might be asking, what then is EMF? Another new term. Okay. So remember I said the potential difference is the work done in bringing a unit positive charge from one point to another in the electric circuit. And I said that this potential difference depends on the EMF. Now, what exactly is EMF? The EMF is simply the potential difference at the terminals of a cell when there is no external delivery in the circuit. What am I trying to say? Assuming you have a battery. Now, let's say this is a battery, even if I can't draw, but let's try to sketch something that looks like a battery. Now, this is usually a battery. It has a pointed side, which we call the positive, and it has a flat end here, which we call the negative. Usually is rated. And if you've seen a battery, especially the ones you use for your remote control, it usually have an inscription on it, 1.5 volts. All right, that 1.5 volts is the EMF. That is the EMF of that cell. Anytime it is not delivering any charge, any current to an external circuit, meaning that the battery, without being connected, as new as it is, has a total electromotive force of 1.5 volts. All right. But the moment I connect this battery to the cell, what happens is that work is being done in that circuit. I mean, the moment I connect the battery to a circuit, work is said to be done in the circuit, especially when the circuit is being closed. All right. When I turn on the switch, then that work done, the amount of work that will be done in that circuit in bringing a unit positive charge from one point to another is called potential difference. And that potential difference also depends on the EMF of this battery. So if the EMF is 1.5 volts, the work done in bringing a unit positive charge from one point to another, which is the potential difference, will also be equal to 1.5 volts. So if the EMF of the battery or the cell is 9 volts, it's equal to the potential difference that will flow through the circuit, which will equally be 9 volts. All right, so that's what I meant by that statement. And we can actually calculate the EMF. We can calculate the EMF by using this formula, that the EMF is equal to work done all over charge. So let's say you don't know the EMF of the cell, but you know how much work that is being done in the circuit, and you know how much charge that flows through the circuit. So we can calculate the EMF of the cell by simply dividing the work done by the charge. And if we say that the EMF is equal to potential difference, it also means that the potential difference PD is equal to work done all over charge. And don't forget, as EMF is measured in volt, potential difference is also measured in volt. And this potential difference is equal proportional to the electromotive force of the cell connected to the circuit. So that's why I said that PD equals work done over charge. So if I'm to use the symbol V, remember potential difference is represented by V. So I can say that V, which is potential difference, is W all over Q. You see that? So V is W over Q. And that is the next equation I want us to take note of. And clearly from here, if I try to make W the subject of the formula, I'm going to have that W is equals to QV. So it's either I say that V is W over Q, or I say that the W is equal to the Q multiplied by the potential difference V. And that is that for that. Okay, so this is the relationship. This is how we calculate the potential difference, knowing the work done in the cell and the charge. The first one, I gave you how to calculate the current when you know the charge and the time taken for the charge to flow from one point to another. Okay. The next thing I want us to look at is resistance. Remember, I'm just trying to pick out the salient points and then give us the equations that are necessary for us to navigate problems involving electric field. All right, resistance, and resistors. What is resistance? Resistance is simply the opposition of electric charge in an electric circuit. The opposition of the flow of electric charge in an electric circuit, or you say the opposition of electric current in an electric circuit, because the flow of electric charge is called current. All right, so the opposition of electric current, this is the opposition of electric current in an electric circuit. So this is called resistance. And then what is a resistor? The device that opposes the flow of electric current is called a resistor. All right. So resistance is the opposition of the electric current in an electric circuit, whereas a resistor is simply the device that opposes what? That opposes the flow of electric current. So that is it. And don't forget, when we talk about a circuit, it's simply a path that is provided for the flow of electric current. So any path through which electric current can travel is called an electric circuit. All right. So the opposition in electric current flow is called resistance, and the device that opposes is called resistor. And this resistor can either be calculated, can be connected in two ways. It's either we connect the resistor in series or we connect the resistor in parallel. But before we do that, before I show us how the connection can be made, I would like us to know the relationship between the current, the potential difference, and the resistance of a circuit. Remember, resistance is the opposition. So how is current relationship between current, which is I, potential difference V, and resistance R? Of course, every one of you that is a good student or that's been preparing for this exam should have known what this relationship is all about. That relationship is called Ohm's law. All right, Ohm's law. So the Ohm's law is the relationship between the law that shows us the relationship between the current, potential difference, and the resistance. And what is Ohm's law saying? What does it state? Ohm's law states that the current flowing through a metallic conductor is directly proportional to the potential difference, provided that temperature and every other physical quantities are kept constant. That is Ohm's law. The current flowing through a metallic conductor. So the relationship I said is called Ohm's law. Ohm's law. Ohm's law. And this states that the current flowing through a metallic conductor is directly proportional to its potential difference, PD, provided, that's a condition, provided that temperature and other physical quantities are kept constant. This is simply what Ohm's law is saying. And this big law, I've seen past questions where students were being asked to state Ohm's law. So just in case it comes up again in your time, you say that Ohm's law states that the current flowing through a metallic conductor is directly proportional to the potential difference, provided that the temperature and other physical quantities are kept constant. What are these physical quantities? Physical quantities like the length of the wire, the nature of the wire, the area of the conductor. When I say wire, I mean a conductor, all right? So the area of the conductor, the length of the conductor, the nature of the conductor, if all these things, and even the resistance of the conductor, if all these things are being kept constant, Ohm's law is going to hold, all right? So provided temperature and those quantities are being kept constant, then we say that the I can write it this way. If that condition holds, we can say that I varies directly with V. So I varies directly with the potential difference V. And of course, in mathematics, anytime you want to remove the symbol of proportionality, you have to bring in a constant K. And in this case, our K is 1 over R. So we can say that I is then equal to what? V all over what? R. You see that? So I is equal to V all over R, which means that, or we can say that V is equal to IR. So this is Ohm's law. It's either you write the equation this way, it's either you write that I is equal to V all over R, which is what we have here, or you write it that V is equal to I multiplying by R. And don't forget that this I is current and the R is resistance, where the V is potential difference. All right, so just like I was saying, this resistor, remember I said resistor is a device that opposes what? The flow of current in an electric circuit. So there are two ways these resistors can be connected. So resistors can either be connected in series or it can be connected in parallel. And when this thing happens, the effective resistance flowing through a circuit is going to be different based on the connection. It differs based on the connection in that circuit. Now, so let's look at resistance in series. Resistance in series. I say resistors can be connected in series or in parallel. So when we say resistors are in series, what does that entail? When resistors are in series, what does that entail? Resistors are in series if they are connected end to end, all right? End to end. So usually, this is a symbol of a resistor. It's either you see it this way, they'll write it this way, draw something like this. So this is a resistor, and sometimes you can see the diagram like this. You have a box, and then you have two wires coming out from that box, usually in this way. So if I have a resistor being connected in series, how does the series connection of resistor look like? So if I use this symbol here, I'll be having something like this. I'll draw that for 3 resistors. So I have 2 resistors. This is one. Then I have another one, let's say coming out like this. I have another one, let's say like this. So if I want to connect these resistors in series, all I'm going to do is to join this end to this other end. Join this end to this other end, such that I have this end to be an outlet that will run into the circuit, and also this point becomes one of the outlets that will run into the circuit. So I can say that these resistors R1, let me call this one resistor 1, resistor 2, and resistor 3, they are connected in series. All right. So anytime resistors are connected end to end, we call such connection series connection. And once they are connected end to end, the effective resistance of these resistors can be obtained by just summing up the whole resistance of each of the resistor. What do I mean? So my R equivalent, let me call it R subscript E, or R total, which is the total resistance in the circuit, RT, is equal to the sum of R1 plus R2 plus R3 in this case. But sometimes you can have more than 3 resistors. So plus, I keep on adding until I get the number of resistors given to me in the circuit. All right. So the point is that if resistors are connected in series, all you need to do is just to add up everything. Add up everything. That becomes the cumulative or the total resistance in that circuit. Okay. So what if they are connected in parallel? Resistance in parallel. So if they are connected in parallel, what happens is that firstly, you need to understand what we mean by parallel connection. So let's say I have a resistor. This is my resistor. I'll arrange these ones like this. This is another resistor. This is another resistor here. And then for me to connect them in parallel, all I need to do is to join all the legs at each of the end, bring them to a common point. So I bring everything here to this common point. And at this point, look at the common point here. I bring out an outlet. So I create another point here where I put all the legs. And from that point, I bring another outlet. So anytime we have such a connection, we say that this is series connection. So in series connection, we say that the resistors are arranged side by side such that their corresponding ends joins together at two common junctions. So that is what parallel connection means. I repeat, in parallel connection, the resistors are being connected side by side. They are arranged side by side such that their corresponding ends joins together at two common junctions. And that's exactly what you see me try to demonstrate here. And then, if these resistors are connected in parallel, how do I find the total resistance in the circuit? So let me call this one here R1. Let me call this one here R2. Let me call this one here R3. And then I want to find the total resistance flowing through the circuit. So what do I do? So it means that I'm going to use 1 over R total. This is how to do it. 1 all over R total is equal to 1 all over R1, which is a fair resistor, plus 1 all over R2 plus 1 all over R3. So it means that from here, for me to find the R total, I'm going to take the reciprocal of the inverse of the sum of the inverse of each of these resistors. So that's what it means. Because firstly, if I find the sum of 1 over R1 plus 1 over R2 plus 1 over R3, anything I get at the end, I'm still going to take the reciprocal again for me to find the R total of flowing through that circuit. And this is how we do it when resistors are connected in both series and in parallel. So I'll just do one example so we go straight into other things, other relationships. So based on this, let's say I have resistors like this. I have 3 resistors. So let's say we have example, we have 3 resistors are connected in series. 3 resistors, 3 ohms, 5 ohms, and 10 ohms are connected in series. find the total resistance, find their total resistance. Without solving, you know what that is. I said, if they were connected, they were to be connected in parallel, what will the total resistance be? What will the total resistance be? Okay, so this is the question. So firstly, they said that the three resistors are connected in series, that I should find the total resistance. All right, so three resistors, 3 ohms, 5 ohms, and 10 ohms. I didn't mention that, please. Resistance are measured in ohms. All right, is measured in ohms, just like we have Ohm's law. So the unit for resistance is what? Ohms. I've mentioned the unit for other quantities we've talked about. So if they are connected in series, I omitted that, in series. Please indicate that. Now they said we should find their total resistance. And the question B, the B part now said, if they were being connected in parallel, what will the total resistance be? Okay, so let's start. Firstly, the solution is a very simple one. Now, they said that R1, let's label them like this. R1 is 3 ohms. R2 is 5 ohms, and then is it 5 ohms? Yes. And then R3 is 10 ohms, and they said they were connected in series. So since they were connected in series, remember our R total becomes the sum of these resistances, R1 plus R2 plus R3. And then if I add everything together, I'm going to be having that my R total becomes 3 plus 5 plus 10. And that will give me a total of 18 ohms, which is the total resistance flowing through the circuit. Now, 18, not 10, please. 18. Oh, okay, 18 ohms. All right. So if then they said, if I connect the same resistors in parallel, what will the total resistance be? All right. So when I connect them in parallel, this is what the outcome would be. So if they were connected in parallel, I'll be having that 1 all over RT is going to be 1 all over what? 3 plus 1 all over 5 plus 1 all over 10. And clearly from here, how would I add up these fractions? I can use my LCM of 3, 5, and 10, and that will give me clearly 30. 3 divided by 30, that will give me 10, and 10 times 1 will give me 10. 5 divided by 30, and that will give me 6, and 6 times 1, that will give me also 6. And then if I divide by 10, I have 3, and 3 plus 1, that will give me equally 3. If I add up everything here, I'll be getting 19 all over 30. So you see that my 1 all over R total, so it means that 1 all over R total alone becomes 19 all over 30. So what then becomes R total? So therefore, the total resistance, which is R sub T, will simply be taking the inverse of 19 over 30, which becomes 30 all over 19 ohms. Anything the answer is in decimal, that becomes the resistance flowing through the circuit. So you see, the same value of resistance, the same value of resistors, when they were connected in series, I got 18 ohms, but when we connected the same resistors in parallel, I'm getting something even less than 3 ohms. You see that? Less than 3 ohms. And that's what we have here. I think this is even less than 2 ohms because 30 divided by 15 will give us 2, and I'm getting divided by 19. So this is about 1 point something ohms. And that is how to do it for this kind of question. Okay. Now, let's look at these factors. These factors that affects the resistance of a circuit. The factors that affect the resistance of current in the resistance that affect resistance in a circuit. Yes. Remember we say that resistance is simply the opposition of electric current. And according to Ohm's law said that the current should be proportional to the what potential difference. But something happens from what we did when we began to extract Ohm's law. We saw that V is equals to what? IR. So, and also I is equals to V all over R. So what happens? What are these factors according to Ohm's law that has to be kept constant for Ohm's law to be obeyed? And we mentioned one of them to be, I said, is going to be the length of the wire, the area, and then the nature of the wire alongside temperature, because the law says that temperature and other quantities must be kept constant. You understand that? So if I keep all those things constant, what becomes? How are they affecting the resistance or the flow of current in that conductor? The first one, factors that affects current flow, or let's say factors affecting resistance in a circuit. So what are the factors affecting resistance in a circuit? The number one factor is the length of the conductor. The length of the conductor. Now, the effect is such that if you increase the length of the conductor, you are actually increasing the resistance flowing, the resistance of that conductor. All right. So increasing the length of a conductor means increasing the resistance of the conductor. What that means is that, let's say you have a generator and then you turn on your generator and you keep the generator, let's say about 5 meters or 10 meters away from where you are, from where it's being connected. All right. So if you measure the current in that generator at the, let's say you use a measuring instrument, your ammeter, you try to check the current the generator is producing on that generator. The current reading will be slightly different as to when you enter your house and then you measure the current at the other end, because for the current to get to your house, it has to travel through a conductor, and increasing the length of the conductor will affect the resistance. It will make the resistance to be what? To be increasing. And don't forget, if the resistance is increasing, invariably the current will be what? Reducing. Because from Ohm's law, we saw that I is equals to V all over what? R. So if this value here is increasing, this one also will be what? Reducing. And if this one is reducing, the resistance is going to be what? Increasing. So take note of that. So one of the factors that affect the resistance of a wire is the length of the wire. So I'm going to write it like this, that the length of the wire, increase in length means increase in resistance, meaning that resistance varies directly with length. Resistance varies directly with length. All right. The next one that affects a conductor is the area of that conductor. Area of the conductor. Area of the conductor. So, what is the area of the conductor? The area of the conductor just simply talks about the thickness of that conductor, how thick the conductor is. All right. So, if the conductor is thicker, the resistance flowing through that, the resistance in that conductor is going to be what? Smaller. So, increase in area means decrease in resistance, which is the reason why you can't use, if you check your power cables, the cable that is being used there are usually very, very tough. They are strong cables. They are not the same one you use in what? Connecting things in your houses, in your rooms, all right? Because it requires more thickness. It requires more thickness to carry more current. Of course, if the resistance is more, if the thickness is more, it will automatically cause the resistance to be what? Lesser. So what I want you to get out of this is that increase in resistance means decrease in area, and increase in area means decrease in resistance. So we can say that the resistance R varies inversely with what? The area of that conductor or the thickness of the conductor. All right. Now the third one is the nature of the material. Nature of the material. nature of the material. So you might be asked to explain or write out maybe 3 or 4 properties that affect, or factors that affect, the resistance of a wire or a conductor. That's exactly what I'm writing out here. So nature of that conductor. When we talk about the nature, we are talking about the material that was being used to produce that conductor. Of course, every one of us here should know that every conductor has their level of what? Conductance. Silver has the highest level of what? Conductance. Is the highest conductor of what? Electricity. Even though it's not commonly being seen because of what? It's high expensive, it's very, very high expensive, and then it can be easily stolen by people. Then the one we have is mainly of the ones made of copper. So the highest conductor, the nature of the material affects the resistance. What that means is that the resistance in silver will be lesser than the resistance in what? Copper. And the resistance in copper will be what? Lesser than the resistance in aluminium, because copper conducts more than what? Aluminium. All right. So the nature of the material also affects the resistance of that wire based on the material that was being used to produce it. A conductor made of silver will have less resistance than a conductor made of copper, because silver conducts more than what? Copper. And that is how it is. All right. So based on this thing, and of course the temperature is another one. The temperature also, if you increase the temperature, you are invariably increasing the what? Resistance. Many of you, I don't know, you might have seen a situation whereby, let's say, in your house or anywhere, the wire start getting hotter, and the moment the wire start heating up, the current begins to get weaker, or the current just shut out from that particular supply, something like that. So what that means is that if the temperature of a conductor is being increased, the resistance will also increase, meaning that there will be more opposition to what? Electric current. So current will not be able to travel effectively along that conductor, because the temperature has been what? Increased. Which is why Ohm's law is saying that provided that temperature is kept constant and all these quantities are kept constant, then the current should vary directly with the what? Potential difference. If those conditions are not being kept, then Ohm's law cannot be obeyed. Now, let's try to combine these two relations here. If I combine these two relations, R varies directly with L, and also R varies inversely with A. Let's combine two of them to set up an equation, another equation. All right. Now, if we say that R varies directly with A, R varies directly with A, and also R varies inversely, no, R varies directly with L. R varies directly with L, which is the length, and also the resistance R varies inversely with the area. So if I combine these two relations, I can say that R varies directly with L and inversely with the area. Of course, I can remove this symbol of proportionality, and by bringing in a constant, which is called the constant of proportionality, in this case, it means that I can write that our R is equal to rho multiplied by L all over A. So the constant of proportionality is called rho. Where that rho, this symbol here, is called rho, R-H-O. It is written like this. So it is not P. It looks like P, but it's not P, just bent like that. It's a Greek letter that is being used in this case to depict what we call resistivity. Resistivity. All right. So the rho there talks about resistivity, and is simply just a constant of proportionality in this case. So take note of that. Take note of this equation. So we've talked about resistance. We've talked about current. We've talked about what again? Potential difference. And I've given us some equations I would want us to really pay attention to. All right. And don't forget that this resistivity depends on the nature of the material. It actually depends on the nature of this material. Okay. So one more thing I would want us to learn. Even though we might not be able to solve equations this night, we might not be able to solve problems. So what will happen is that I want us to take note of the formulas, these formulas, from our next class, which will be on Friday. What I will do is that I will be solving problems, past questions. I'll gather as many past questions as we can see, or as I can get, based on this topic, and then we'll try to see how we can use the formula in solving the problem, both the ones that involve circuit diagrams and the one that may just come in words. All right, but before then, I want us to take one more equation, having established Ohm's law. Remember I said, recall that I said that work done in a circuit, or as when I gave you this formula, that V is actually work done over charge. All right, when I defined EMF, and then I say EMF, or the potential difference, is equal to the EMF of the cell, I said that V is equal to W all over Q, where V is the potential difference, W is work done in the circuit, and then the Q is the charge. So from here, I can say that W is equal to QV, the Q charge multiplied by the V. But clearly, from the first equation, remember we said that V is equal to IT. No. Remember we said that Q is equal to IT. Remember I told you I becomes Q all over T. And then if I make substitution here, it means that if I cross multiply there, it means that Q is going to be what? IT. So if I replace this Q with IT, I'll be having that W, which is the work done, becomes I multiplied by the time multiplied by the V. Or let me write it more conventionally. We say that W is equal to IVT. So this is also how to calculate the work done flowing, the work done in a circuit, or the energy that is flowing through that circuit. So if you're asked to find electrical energy or electrical work done, you can equally use this formula that W is equal to IVT. That's when you know the current, the voltage, and time. Or you can also use that W is equal to QV, where you know the charge flowing through the circuit and the potential difference. All right. But also from your Ohm's law, we've also established the fact that from Ohm's law, we said that V is equal to IR. So it means that I can replace, and now I'm having that W is equals to IVT. So I can replace V with IR. All right. So if I replace V with IR, I'll be having that this implies that the W, the work done in the circuit, will be given as what? Current multiply another current, so I square RT. So this can also be used in solving the electrical work done or the electrical energy that is being done or being produced in that circuit. So these are relationships based on the parameters I'll be given. So if I'm being given the voltage and time, I can use IVT. If I'm being given resistance, I can use I square RT, where the V, or the potential difference, is not being known. So take note of this equation. I've given you how many equations now? Even though we might not apply them tonight, but in the next class, I won't go back to the equations again. I will assume we've known them already. So this is my equation 1. No, this is not the first equation. This is the first one. This is my equation 1. This one is my equation 2. Then moving down, this is my equation 3. Or this one, the fourth one. Then still moving from Ohm's law, we got equation 5. Or this other one, which is still Ohm's law, another way of writing it, let me call it 6. And then moving down, for resistance in series, we saw how that can be connected and that of parallel. how we can calculate effective resistance. Then, based on the factors affecting resistance, we saw this one, which is equation 7 now. And then we went back, we found equation 8 from the one we already found before, V equals W, W equals Q multiplied by the potential difference. And from there, we now found this one, that W is also equals to I square RT. And then one more thing, which is I've talked about the work done. And don't forget that this work done depends on energy. So whether they ask you to find the work done in the circuit or they ask you to find the energy that flows through the circuit, the formula is always W equals I square RT or W equals IVT. Also, W equals Q times V. It all depends on the parameters you have been given in that very question. But the last thing I would like us to look at is the electrical power, the power that flows through the circuit. If you can find the energy, you can always find the power, because we say that power is the rate at which work is done. So it means the electrical power, P, power generally, is simply work done over time or energy over time. So if I put in these formulas, where W is IVT, so I'll be having that this becomes IVT all over T. So it means that power becomes what? IV, because the T cancel out what? IV. You see that? So this is the first equation for power, the first relation. But if I'm using I square RT, so it means that my power become I square RT divided by what? T. Again, the T cancel out the T. I'll be having that electrical power P becomes I square multiplied by R. So this is another relationship that is being used to calculate electrical power in an electrical circuit. So take note of these things, as they are very important, so that by the time we begin to engage them, it doesn't look like anything new is being done. And at this point, I would like us to ask some questions. I know I've really said a lot. As I do say, you can always go back. I know sometime or somehow I'm not slow. I can be fast. The reason for being fast is because we don't have as much time. And I really want us to cover as many as is required in a given topic. That's why you see me sometimes speeding up. But you can always go back to the video. Go back to the video in less than 24, in less than 12 hours. In fact, in the morning, I should have uploaded the video. So you can always go back and check anything that looks like confusion and clear it off. So that by the next class, you're already used to the formulas and we can engage them in solving practical exam questions. Whether the one involving circuit diagrams, the one involving words, I will show you different kind of questions, and then we'll work them out using these equations. At this point, I will just want you to ask a question, just in case you have any. Does anyone have a question? It's true that you guys are already, you've gotten used to the fact that when lectures like this are going on, you just sit back and listen. And me, myself, I've gotten used to teaching without asking questions, because you guys have always been like that. But it makes sense when there are interactions. So you always know how to ask questions. It helps you understand something you might not have known as the teacher is explaining, or maybe you have a feeling that maybe something is incorrectly explained or you didn't get it correctly. You can always punctuate and then ask a question and get better understanding. So if there's no question, we may have to just bring the class to a close. So if you understood, if you gain from the class, I just want you to react. Just indicate react. That shows that you really benefited from the class. All right. All right. So thank you very much. In the next class, what we'll do is just to solve problems using these equations. I think I've given up to 10. There are about 10 equations or even more. So even though they are very simple equations, you can see they are not so complex. Just ratio this times this over this, like that. So we'll meet in the next class. Have a wonderful night, everyone.